looking at the next few problems, we see the same kind of problems. And what I would encourage you to do is pause and try to go through these problems on your own and then kind of check back and see how you did. So for the remaining problems, I want to try to chunk these problems so that you have a nice procedural way to approach these problems, just a general way for any of these optimization problems. And the way that we'll chunk them is we will have a first stage where we set up any equations that we need, and often that will involve diagrams. And then the second stage will always be the first derivative test, because once we get the function we need, then we can optimize it. That is to say, we can find any maxima or minima, and then the last stage will just kind of be to answer the original question. So what is the minimized cost? That, that kind of thing. So let's go ahead and do that for each of these problems, and we'll kind of work in a nonlinear way. So we'll go through each of these and first set them up and get the equation that we need, and then we'll come back to each one and then do the first derivative test and finish them up. So for this first one, no diagram necessary, and it kind of wouldn't help us here because this isn't really a geometric physical type problem. So we're talking about producing strollers here, and we have this demand function. This gives us the quantity of demand based on price, and we want to know what price will give us the greatest annual revenue. We're reminded that revenue is price times quantity. So this one is pretty direct. Other questions we may need to remember the revenue formula, so make sure you have that in your toolkit, but let's go ahead and just write that down. Revenue is price times quantity. We see the same problem here. This is the thing we want to maximize revenue, but we have two variables. But given this demand function, if we make that substitution for Q, we get on the right hand side P times the quantity 300,000 minus 10P squared. And we can then distribute that because we know we're going to want to take a derivative. And so now this is a function of only P. And so we can take derivatives of functions with one variable. So if you take further calculus classes, you'll find you can actually take derivatives of functions with two variables, but there's a little more work involved there. So I've just added some details just to make this consistent with our previous understanding of these problems. So our objective function, the thing we're trying to, in this case, maximize, is revenue, and then we're using this constraint about the demand based on the price to update our revenue and make it a function of only one variable. So now we're ready to take derivatives and apply the first derivative test. So let's go ahead and do this for the remaining problems, and then, like I said, we'll come back and look and finish that problem. So this problem, go ahead and pause and read through it, is a little different in that we're again building a fence, so very different actually from the last problem, and a diagram is helpful here. So we're building this triangular fence, and we get to assume that it's a right triangle. The idea is that we have a nice stream on the one side, and we're going to build fence on the remaining two sides. And then we're told this information about costs. So on one side we'll have a cost of a certain type of fencing, which is $5 per foot, and on the other $1 per foot. It doesn't matter which side we choose in a problem like this, because our labels will kind of match up with however we assign those prices. So we always want to label our diagrams with lengths. So it would be strange for us to label these with a rate of cost or something like this. So $5 per foot doesn't really make sense as a label. So triangles we're usually labeling, we're calling those things base and height. So let's call this B and H. Just as a reminder, I'll write feet here. So our objective function is, in this case, area, because we want the biggest garden possible. So you just have to look for that language. So you see here in the last sentence, we want to have the biggest garden possible. So area of a triangle is, we'll call that A, 1/2 the base times height. So you just need to know areas for this course of triangles, circles, and rectangles. So nothing too terrible. What is our constraint? So we're constrained by our budget. We have $100 to spend. We want the biggest garden, so we'll spend all of that money. So we need our total cost of fencing to add up to $100. So how do you think about this? Well, you can always think about a toy problem. So for example, if this side B here was going to be $1 per foot, then if you had 10 feet of it, it would cost you $10, right? How did you do that? You said 10 feet times $1 per foot, right? That tells us that, so instead of 10 feet, we have B feet. Then our mathematical expression is 1B, or just B, for that cost of that length of fence. Similarly, we have H feet of the other side, and it's $5 per foot. So to get the total cost, we multiply our amount in feet times our unit cost. So this would be 5h. Now if you set it up 5b plus h, so if you flip how you assign those costs, that will be fine. You'll still end up with the same final answer. Okay, now that we have our constraint, we can solve the constraint. In the last problem, the constraint was already solved for one of the variables, but here it's not. So just subtract 5h from both sides. If you want to solve for h, you could, but b is quicker to solve for. So this then we can substitute into our area equation, and now we have area in terms of only h. So 1/2 b times h, and b is 100 minus 5h. So we're going to apply the first derivative test, and so we definitely want to clean this up and simplify it beforehand. That will generally make your derivative a lot easier. So I distributed twice here. So you have to distribute the 1/2, and then you also need to distribute the h to each term. So when you do that, you'll get 50h minus 5/2 h squared. So hopefully you're starting to get a feel for the general pattern of finding the objective function and the constraint, and solving that objective function for just one variable. Alright, let's set up the other ones and then we can come back. So this again is a problem from the textbook. So hopefully you're seeing a pattern that these problems are coming from the textbook, and these are important problems to look at and study. Alright, so we're looking at cans for this problem. We see that the can has a capacity that's fixed, and then we're asked what height and radius should the company use to minimize the amount of material. So again, this explains why we will take this approach, because we're looking to minimize some quantity. So in general, if you want to optimize, you just use the first derivative test. But for problems like these, when you write out your objective function, you'll have more than one variable, and that's the clue that you need to do a little more work. So as I mentioned previously, I'll always provide you with any volume formulas that you need. So the capacity is another word for volume. So we're dealing with volume here, and volume of a can is pi r squared h. And while we're at it, we may as well draw a picture of a can or a cylinder. And so if we call this radius r and a height h, then that represents our r and h in centimeters in this case. So we're told that the capacity or volume is fixed, and so that means on the left hand side of this first equation we should have 354.88. The thing that we're trying to minimize, so this is our constraint, and the thing that we're trying to minimize is surface area. That's the amount of material. So to find our objective function, we need to build a surface area equation. That is the amount of material, so you can imagine that's the amount of wrapping paper you need to wrap this, or the amount of paint you would need. In other words, it's an area, so we need to lay things flat to really get a good idea of what this area is. So you can see I've went ahead, and this is supposed to be a pair of scissors, if you can't tell what that is. But imagine cutting this can up, cut the top off, cut the bottom off, and then take the cylinder and cut it vertically and unroll. So just like kind of a toilet paper tube, unroll that. And I've copied down the labels that we have. So circles have area pi r squared. So these areas we already know. So if we call the radius r, then these areas are pi r squared. So we have two of those. So let's call our surface area, our amount of material equation, S, and so we need two of these pi r squared areas. And then the rectangle here has a height h, but we don't necessarily have the length. But if you just pause and think about it, this length has to wrap around each of the circles, the discs that form the top and the bottom. So this means that this dimension has to be the circumference of our top and bottom, which we remember is 2 pi r. So this area here of the tube portion that we unroll will be 2 pi r h. So just multiply the side lengths. And then that finishes our surface area equation. So as we see, the surface area depends on r and h. Don't forget pi is not a variable, so there are actually only two variables there. Sometimes we get confused by that. And so we need this constraint. We need to solve this for one of the variables. So let's solve this for h. Dividing both sides by pi r squared, you'll get that h equals 354.88 divided by pi r squared. And now we can substitute that into our surface area equation, and we're ready to apply the first derivative test. So we substitute that, and we could simplify things a little bit, because we see in the second term that we have a pi in the numerator and the denominator, and we have 1r in the numerator and 2 of them in the denominator, so we're left with 1r in the denominator, and that can be written as r to the negative 1. We're doing that because that will make the derivative easier. So this sets up problems 1 through 3, and it gives us the objective function in terms of one variable, and now we can apply the first derivative test. So let's go back and start finishing each of these problems. Problem 4 I'll leave for you to try on your own, so give that a try if you haven't already been trying these, and check back with the solution to that in the annotated notes. Alright, so we're back to problem 1, and now we can apply the first derivative test. And let's just make a note so that we remember what we were doing when we did this. So for the first derivative test, the first step will always be to take the derivative of your objective function and then set it equal to 0 and solve for that variable. So taking the derivative, setting equal to 0, and solving gives us 2 critical points at plus and minus 100. This is price in dollars, and so the negative 100 is non-physical, so we won't check that. Next, we make our table to classify this critical point to see if it's a maxima or minima or neither. We assume that this is going to maximize revenue. That's what we're looking for this problem. But nonetheless, we need to check. So we make our table. We include our critical point at 100 and a test point to the left and to the right. And we plug those test points into the derivative and check the sign. So if you go ahead and plug those back into your derivative, then what you'll see is that you should get a positive and then negative sign. This tells us that the revenue, R, is increasing, then flattens out, then is decreasing. And that is to say, revenue is maximized at a price of $100. So just a complete sentence to finish this problem: a price of $100 will maximize revenue. Coming back to number 2, we had an objective function where we were trying to have the biggest garden possible, so that means we want to maximize area, and so we took that constraint and solved area for reduce the number of variables in the area to just one variable h, and so now we can apply the first derivative test. So the first step is always to find any critical points of our function, so we take the derivative and get 50 minus 5h, and then we set that equal to 0 and solve, and so we just have one critical point at h equals 10. So now we need to classify the critical point, and so we include our critical point at h equals 10. We know the derivative is 0 there, and then we take a test point to the left and to the right, and if we plug in 9, we'll see that we have a positive value, and plug in 11 and you'll see a negative value. And so what this tells us that h is increasing, flattens out, and is decreasing. So in other words, area is maximized at a height of 10. So now we need to find the base, but we can do that with one of our equations that we already have up here. We found, based on our constraint, that our base was 100 minus 5h. So we just plug in 10 for h, and we can solve. So we get a base of 50 feet. Now we just need to put all of this together and summarize our results. Alright, so we need to provide 2 details. So one is the amount of fencing. So we already found that we need 50 feet and 10 feet for our base and height respectively. One thing that you want to pay careful attention to is which side length is associated with which price. So if you come back up to our constraint equation, we associated the length of B with the $1 per foot and the length of H with the $5 per foot. So you do have to pay attention to that when you give your final answer, otherwise you may flip things accidentally. So that's what we have there. And then the last question was what is the size of the enclosure? What area does it enclose? So just a quick sentence there, and we just plugged in our base and our height into our area equation and found 250 square feet for our final maximized area. Finally, we come back to the cylinder problem, and we've already done most of the difficult work with the diagrams and updating our surface area equation. So now we'll again just apply that first derivative test and summarize our results. So as we saw, the first step will always be to find any critical point. So again, that means to take our derivative and set it equal to 0. Okay, so we take the derivative just using the power rule, and we already had s into, we set that up so it was nice to take derivatives by moving that exponent up and making it r to the -1. So we take the derivative and we set that equal to 0, and you can see that the last term I rewrote as an equivalent fractional term, because generally negative exponents, we want to get rid of those when we're trying to solve for the variable. So now we can go ahead and add the negative term to both sides and solve for r. Okay, so when you solve for r, you should end up with about 3.84. So remember, when you're entering this into your calculator, to put parentheses around the denominator term, so around the 4 pi. Otherwise, it will just divide by 4 and then multiply by pi, and also to put parentheses around your exponent term, the 1/3 in this case. So the next step is to classify the critical point and see whether this is a max or min or neither. So the table is what we'll apply. So as usual, we include our critical points and then a test point to the left and to the right. And so for this problem, 3 and 4 are fine for test points. And plugging those into the derivative, we see that the derivative changes from negative to positive as we sweep through that critical point. And so that means the surface area is decreasing and then increasing. And that is to say, surface area is minimized at this critical point. So the last step is to find the height, the corresponding height. We already have the radius, so we don't need to do all of this work again. We can just check our work from the beginning, and we have, if we go way back to the top, we have this constraint equation that we solve for h. So we have h in terms of r, so we can just plug that in and find our h. So rounding to 2 decimal places, we see that the corresponding height that will minimize the surface area is 7.66 centimeters. So we just finished this with a sentence to summarize our results. All right, so there's one more problem left, and as I said, go ahead and give that a try on your own. So go ahead and pause, and I'll provide the solution now. So there you have it. Hopefully you were able to solve this on your own and you're getting the hang of these. Make sure to check out the suggested problems on the course website. Let your instructor know if you have any questions.